the autoionization constant, what is it? That is the Ka value. And what the video for this is to figure out what it is and what it tells us about an acid. All right. Now, acids are typically just broken up into two categories. You got your strong and your weak acids. All right. Quintessential strong acid is hydrochloric, and a good weak one is acetic acid. Now, the difference of these two acids is when I dissolve them, let's say I put 5 in, or let's just go 4. For every molecule of HCl, it's going to completely ionize. I'm just going to do 3, all right? Because that's a strong acid. It's always going to dissociate. It's going to make H plus or H3O plus. Right? It's probably going to combine with water to make that, rather than just have a proton floating around. So it's going to completely do that, whereas the weak acid will partially make its conjugate base and the hydronium, all right? All right. The other two will not dissociate. They will stick together. Okay. Sometimes the molecules are written like HA, just to simplify, where A is your acid, your anion, or your conjugate base of your acid. Okay, so strong acids completely dissociate, complete dissociation, or ionize, and I spelt that wrong, all right, where weak acids will partial dissociation or ionizing. Therefore, weak acids have what is known as a Ka value. This Ka value is it's the autoionization constant. It's generally for weak acids. It's going to give you a sense of how much of the acid is dissociating. The bigger the value, the stronger the acid, and as Ka goes up, pH goes down. All right. Now, these values are going to be in the back, like in a table somewhere. They'll be given to you. This is, for example, acetic acid is this. Phosphoric acid, the one that's in Coke, is this. All right. Now, this Ka value is an equilibrium constant. It's for a weak acid. There, it's its formula right there. So I'm going to show you the formula in a second, but it's on our reference sheet. So you don't need to memorize this formula. You're going to just need to know what it means. And this video isn't really about like using the formula. It's just about what the constant means and what it tells you about an acid. So the Ka here is the formula. You've got your concentrations of your conjugate base and your hydronium over the concentration of the acid itself. And that comes from writing out the expression like this with water. All right. Now if I had an acid like acetic acid, it's going to form hydronium plus acetic acid, acetate ion. All right. So this formula, this Ka value, would be equal to concentration of acetic acid of the original solution all right, like that. That would be what it would equal to. And that was one of the ones we looked at. Acetic acid is 1.85. That would go there. Okay? And in another video, I'll show you how to do the math. But this video is just really about a Ka value gives you a strength of a weak acid. The higher the value, the stronger the acid. It also means that for these acids that have Kas, they're not completely dissociating, so their pH will be less than you'd expect based upon their molarity. Whereas with a strong acid, the pH is going to completely dissociation, so the concentration of hydronium will be equal to the concentration of its molarity. And let me give you an example of what I mean. HCl. If it's 1 molar, when I dissolve it, the molarity of the solution, the concentration of the hydronium is 1. Okay? Therefore, the pH of this would be equal to 0. All right? Because the log of 1 is 0. All right? I don't know that I said that right. The pH, the negative log of the concentration is 0. Okay? So pH is 0. However, with acetate, or with acetic acid, if I have 1 molar, it's not going to completely dissociate. So you would expect the concentration of H3O plus to be actually less than 1. You would need, because not all of this is going to dissociate to make H3O, to make hydronium, to make H3O plus. Some of it's going to remain bound to its anion. Therefore, you'd expect it, so you'd expect your pH to be less than 0, or not less, but greater than 0, right? And in fact, I think the pH of this solution is roughly about 3.2. I'd have to look it up. But this is not about that. That's in for another video. Okay? Hope this helps. Bye.